Hey guys, what's up? Welcome back to our channel. So apparently we're making fuel cells for our school lobby because it has pretty bad ventilation, and we should get a cell suitable for supplying electricity to a ventilation fan. So what we're going to talk about today is formic acid fuel cells. Formic acid is just methanoic acid, they are equivalent. So why do we choose this? Well, because of its safety measures. And this cell works under a very safe temperature, which is around 40 degrees Celsius, so it won't overheat, it won't explode. And methanoic acid is safe to handle. We have handled it a few times in the lab already. And the transport of these fuels are very safe for the same reason. And second of all, the power. So a typical electric fan uses around 40 watts, and this cell has a power output of 50 watts, which is surely enough to power up the fan. Another reason is that the cost is very low, and this cell is already broadly in use. Last but not least, this cell clears hydrogen fuel cell, and this is because the methanoic acid is much easier to transport, as I just mentioned, and it is much easier to store. Unlike hydrogen, this methanoic acid is in liquid form, so we don't need to use a high pressure to store the hydrogen gas. So it is in turn much safer. Also, this cell has a much higher theoretical energy. You can look at the EMF, which we will pass on the time to Toby, and he will talk about it in detail.
Now, let's talk about the mechanism. At the anode, formic acid is split into two protons, which are hydrogen ions, and two electrons. From this equation, we know that oxidation takes place because the oxidation number of carbon increases from +3 to +4. The observation here is effervescence due to the formation of carbon dioxide. Moving on to the cathode, reduction takes place because the oxidation number of oxygen decreases from 0 to -2. This reaction takes place at room temperature, so water is formed. Therefore, critical water management is required for the long-term performance of this fuel cell and to avoid flooding. After balancing the number of moles of electrons, we can get this overall equation. Finally, let's talk about the catalyst. Platinum is a solid. It is involved in forming a carbon monoxide intermediate. Now, let's play this question.
Let's move on to the drawbacks of DFAFC. The first challenge that it is facing is the mass transportation limitation. High concentration of formic acid damages MEA, which is a core component of a fuel cell. The second one is catalyst poisoning. If platinum is used as a catalyst, it will have a low efficiency and it will be relatively expensive, while palladium is cheaper and has a higher efficiency, but it deactivates during formic acid electrooxidation. There is some future development that we expect to see. We suggest some improvement to enhance the performance and the commercial values of DFAFC. Implementing DFAFC can also promote SDG goals. And finally, there are some AI-generated examples of DFAFC. Thank you for listening to our presentation.